spend some time on abstract beauty, because I think simply being engaged in inquiry in an open-minded way, you're also making society better, perhaps in a slightly roundabout way. But given how rare open-mindedness and inquiry are in our society, I think modeling them is important, whatever it is that you're inquiring into. Anyway, so that said, this talk is not completely divorced from the real world, but it is what you would call let's call it a machine learning theory talk. So I will be looking at a kind of toy case of an important problem. Okay, I'll stop apologizing. All right, so let's start with a problem that in one way or another, thousands of people solve every day. So suppose we have a matrix Y, and this is our matrix of data. And we believe that what this matrix has is some kind of ground truth in it, which is rank 1. Of course, we might involve, I told you it was a toy version. We'll start with rank 1. So what I mean is, I think that this matrix is basically the outer product of some vector with, well, itself, because I like symmetry. So that's the case I'll look at, where this vector has some length. Let's say that we are in n dimensions. So this is an n by n matrix. And I'm going to choose a normalization in which this vector has length squared n. And then that's going to be multiplied by some constant, which is like how strong this ground truth rank 1 pattern is in the matrix. And then there's going to be a bunch of noise. And the noise is another n by n matrix where each one of its entries is normally distributed, mean 0 and variance 1, but also to maintain the symmetry, I'll assume that this is symmetric. If you are a random matrix geek, you know that the variance is 2 on the diagonal, but we won't pay any attention to that. Okay. Now, what do I mean by this notation? You may or may not have seen that little cross with a circle in it. That's meant to be an outer product or a tensor product. But I mean simply this, that Yij is Vi times Vj times lambda plus Wij. Okay. Now, if I promised you, so if I send you a matrix and I promise you that it was made in this way, and maybe I promise you even more, I promise you that what I actually did, I'm playing the role of nature here, is that first I chose the vector v. Maybe I chose it uniformly from the sphere of radius squared n. And then I chose all this Gaussian noise, and then I sent it to you. Okay. So, we're in kind of Bayes land here, right? I mean, Bayesian inference is great, but the weakness of Bayesian inference is that you really have to commit to, you really have to believe or temporarily assume some model for your data. So that's where we are. And then I say, hey, can you reconstruct this vector v for me, at least approximately? Well, what would you do? You would do principal component analysis, or to be less fancy, you would just diagonalize this matrix. It's a symmetric matrix because both the signal and the noise are symmetric. And then you would look at its eigenvector with the biggest eigenvalue, and you would hope that that eigenvector would be close to v. Okay. So how many of you already know this whole story?
Up until now.
Up until now. Okay, all right. All right. Well, so the wonderful thing is that random matrix theory lets us know exactly when this approach works and how well it works as a function of the signal to noise ratio lambda. And because, I fixed the variance of the noise. So suppose that we didn't have this signal at all. We just had the noise, a null model where it was just noise. Then it is a beautiful, wonderful, super fantastic fact that everyone should know that if you make a large n by n matrix out of Gaussian noise like this, and it's symmetric, and then you look at its eigenvalues, it has a distribution of eigenvalues, many eigenvalues, and if you make a histogram of them, you get this semicircle. And before you go home tonight, take Maple or Mathematica or what have you, just make a 20 by 20 random matrix with independent normally distributed entries, maybe average it with its transpose to make it symmetric. I guess you have to multiply by a square root of 2 to do that. And then just tell the computer to give you a histogram of its eigenvalues, and you will already see this beautiful semicircle emerging. There are many proofs of the semicircle law. It goes back to the physicist Wigner, Eugene Wigner, who used random matrices to think about complicated atomic nuclei. There are at this point many proofs from different points of view, group theory, combinatorics, and so on. All right, so this is the spectrum of this matrix that you would get in the null model where there is no signal at all. The signal is then, we could call it a rank 1 perturbation to this random matrix. And when lambda is big enough, what happens is that in addition to the semicircle, there is a new eigenvector sitting out there. And the eigenvalue, which I'll call u, well, we can actually analytically compute the accuracy, if you will, the inner product between u and v, or if you prefer the cosine similarity or what have you. And so we know that there's a critical value of lambda above which this thing appears, and we know this accuracy. I guess I should divide by n or something. We know the accuracy goes like this, up towards 1. And below this critical value of lambda, something kind of profound happens, which is that this gets lost in the noise, or in the bulk, as we call it. And in here, these eigenvectors they're random vectors. They point in all directions, except they're orthogonal. And you really can't learn anything, actually. So in fact, friends of mine showed that it is information theoretically impossible in the limit that n, the dimension of this matrix, is large, to get any reasonably good estimate of v. In other words, in high dimensions, any vector who's even with just 89 degrees away from v. Okay, it is even worse than that. You can't even tell whether the signal is there at all. You can't even distinguish this model from the null model, where it's just noise. Okay, so that's pretty interesting. And what it tells us is that at this phase transition, we go from this problem being easy, namely there's a spectral algorithm, which gives us a reasonably good estimate. But below that value, it's impossible. And again, this has nothing to do with how powerful your computer is. It's just the information isn't there. If nature, I'm trying to send you this message, but I'm sending it through a noisy channel, it just doesn't get through. The information is not present in the data. Now, I should mention that what I've told you about this nice clean phase transition does rely on the prior distribution here just being uniform on the sphere. Okay? If you knew something about this vector, or you believed something about it for external scientific reasons, for instance, if you knew it's very sparse, if you knew that only 3% of its entries are non-zero, then you could do other things. Although the interesting thing is that this algorithm, PCA, just look at the dominant eigenvector, is the only polynomial-time algorithm, the only efficient algorithm we know of, even when there is that more sparse information in many cases. So, and now what happens when there is a strong prior on V is that this impossible region goes down because there are lower values of the signal to noise ratio where you can figure out the vector, but we think that doing so requires exhaustive search, roughly speaking. And so in between, we believe that there is this hard regime where, yes, it's information theoretically possible. Some people call it statistically possible, but we believe it's computationally hard. Many people call this a statistical computational gap, where statistical means what you can do with arbitrary amounts of computation, given the information available, and computational is what you can do efficiently. Now, we don't know that P and NP are different if you hang out with computer scientists. So we currently have no hope of proving that there is no polynomial time algorithm that works in this regime. But we can hope to show that many of our favorite algorithms fail. Okay. And hopefully even large classes of algorithms fail. All right, so that's the matrix situation. So like I said, the matrix situation already gets quite interesting if you have some strong prior here. But the tensor situation gets interesting even without that. So what do I mean by a tensor? What I mean is that, for instance, I now have a thing with 3 indices like y, I, j, k, and what I mean by the p here is usually 3, but p will be the number of indices. Some people call it the number of legs. I read once that the inventors of Dungeons and Dragons were not sure if they wanted to use the word level for both spells and characters, and they had like order and degree, and then they said, let's call them all levels. So if I say high dimensional tensor, I don't mean it has many, many indices. What I mean is that it's like n by n by n, where n is large. Okay. So let's say that y is v tensored with itself 3 times, and plus lambda plus w. And this is a tensor of noise, and it is again going to be normally distributed, and it is again going to be symmetric, but now, symmetric if I permute these 3 indices in any way, just to keep things nice and symmetric. Everything I'm saying about the non-symmetric case where these vectors might be different also holds. It's just the symmetric case is pretty. All right.
And it will also hold for tensors of higher degrees, right? So I can have a tensor, a formal tensor.
Yes. 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 You call them modes? Okay. Why? All right. Okay. So this problem is called tensor PCA. And it is often credited to Montanari and Richard for writing it down. But it is a kind of tensor factorization, right? So in particular, suppose that you believe this model and you want to find the maximum likelihood estimate of V. Well, that means since Gaussian noise has a likelihood which goes like the sum of the squares of the entries of the noise, because these are independent Gaussians, well, maximizing the likelihood means minimizing the squared error between y and this factorization. Okay, and so some of you I know have been interested in this kind of problem, and there are lots of approaches to this. So at first you might think, oh, well, this is just a least squares problem, it's just some linear algebra problem. But in fact, for tensors, this is quite tricky. There can be many, many local optima in general. I'm not saying that will be true for real data, but it is possible in general. And so if you run some iterative algorithm like we were talking about this morning, that kind of repeatedly tries to minimize this by adjusting one component and then the other component and then the other component going back and forth, well, it's an iterative algorithm which can end up in many different places, which are many different local optima of the L2 distance or of the probability. So what's happening is that, the wonderful thing about about the eigenvector decomposition, or more generally the singular value decomposition, is that for matrices, this is, first of all, a simple convex problem where you can just zoom straight to the optimum that minimizes the L2 distance using linear algebra. It is worth, by the way, it is worth proving that the closest in L2 distance low rank matrix to a given matrix is the but for tensors, it's some crazy bumpy matrix in high dimensions. And with lots of local optima, and finding the global optima might be hard. It's worse than that. So let's call this, I mean, this is some kind of rank 1 tensor, right? So in general, suppose that this is my description, U tensor V tensor W. This is my definition of a rank 1 tensor. And let's define the rank of a tensor as the smallest number of rank 1 tensors. The smallest number of rank 1 tensors it takes to add together to get your tensor. Right? That's analogous to the rank of a matrix. Computing the rank of a tensor is NP hard. Okay, isn't that crazy? So a lot of the linear algebra we might like to have is just not really there for tensors. And why is that? So for tensor PCA, it's very reasonable to say, well, can't we do what we did for matrices? Look at the spectrum. Okay, just look at the eigenvalues. What's an eigenvalue of a tensor? What's an eigenvector of a tensor? So I think of this like yijk as a little thing with 3 legs coming out of it. Okay? And you can do things like this. Like I could put a vector here. Okay? I could put a matrix here. And then I could contract this. And what does that mean? It means summing over all of these indices, where this index applies both to y and to m and so on. So this remember, this is symmetric anyway, and then MIK. Okay. So you can do all sorts of generalizations of matrix multiplication and taking traces and so on, but you can generalize them and put them in this graphical form. That's what we'll do. But you could, of course, take this lovely 3-legged creature, kill it, stick a pin through it, and then put 2 of the legs this way and 1 leg that way, and then call it an n squared by n matrix where I and j are over here and k is there. You could look at the singular values of that n squared by n matrix. But if instead you had squashed it into your display case a different way and put j over there, those singular values might be totally different. I'm making fun here because lots of algorithms involving tensors work by squashing them into matrices and then just running all our favorite algorithms on the matrices. And you can make progress that way. But it feels wrong, doesn't it? This thing should be allowed to wave its tentacles and join with its fellows. Okay. All right. So, indeed, this is the kind of thing I'm going to write, but I can ignore the sum using the Einstein summation convention of general relativity. You can impress your friends with this stuff. I can say, well, this is a little network. It has 1 tensor with 3 legs, or modes, as you say. It has a vector, which of course is a tensor with 1 leg, having 1 index. It has a matrix, and then we contract. Okay, good. So let me tell you the kind of phase diagram of this problem. And it's a little bit like the matrix PCA with a complicated prior. But so here, I'm going to stick with the spherical prior. So everything here is rotationally symmetric. The prior is the same, and I didn't say this before, but a marvelous fact about these Gaussian noise tensors is that if you change basis, the whole thing, the distribution stays the same. Okay, because of the spherical symmetry of the Gaussian distribution. So now what happens is that as a function of lambda, our signal to noise ratio, we have this easy regime, an impossible regime, and this we know it's possible, but we think it's hard regime. And here, this is what happens when lambda, this isn't like a super sharp thing, but really, I'll just write it down. If p is the number of legs of the tensor, the number of indices, then this happens to be at n to the minus p over 4 in this normalization. And this happens to be at n to the minus p minus 1 over 2. And if you're better at arithmetic than I am, you'll notice that these are the same when p equals 2. So for the matrix case, these go like that. And we just have easy and impossible with PCA. But for p greater than 2, there's this intermediate thing. Okay. Now, why? So again, we know below here is information theoretically impossible. Above here, we know that there are spectral algorithms that work, including flattening the tensor into a matrix and looking at its spectrum. That does in fact work. You sometimes have to do a kind of repeated unfolding thing, but I won't go into it. But so up here, it's easy.
Do you put parafact on the easy side?
Do I put what?
Do you put parafact, right? There are equivalents of PCA factorization in tensors, or like.
Right. Parafact is one of the iterated. I actually, I expect that works at this same point. I don't know when it works. That's someone must know this. There's also something called tensor power iteration, where you choose some random initial vector, and if you have 3 legs, you put it on both legs of y and then get a new vector, and then copy that vector and do the same thing. And so this is like powering up. Oddly enough, we now know that this does not work all the way down to this point. It requires, this particular algorithm requires a larger signal to noise ratio. In other words, this algorithm is not optimal, even though it's easy to run and quite popular.
As is parafact for tensors.
Yeah, right. The funny thing is, like, this work comes from a little sub-community which is not necessarily tied into the data science community where everybody knows what parafact is.
So for the audience, like PCA, you do. So if you have a matrix, you do PCA. If you have a tensor, you would do parafact. You have a tensor. If you have a matrix, then you do singular value decomposition. If you have a tensor, you do Tucker decomposition. And then the parts that decompose are similar, have similar meanings to when you do, for example, single value decomposition on a matrix, where you get your U, your sigma, and your V. So you would get like a tensor core, right, of how strong the concepts are, and then you get these factor frequencies, for example.
Right. But I guess the difference is that in the tensor case, these algorithms really are iterative. They're not just sort of one and done like the singular value decomposition is. And so they can arrive at different places depending on how you initialize them.
Yeah. And as a true computer scientist, I'm fine with that, as long as it's a good minimum.
Right, yeah.
Right, but as a theoretician, you're like, wait, what?
Well, and honestly, with real data, with a strong ground truth, these things will work most of the time. Yeah. I mean, this is maybe a little unfair, but you could say if the signal is strong and really there, it's easy to find. Now, I'm not saying that there isn't a lot of technical cleverness in finding it, but I'm just saying that Like if there might be local optima, but they might all be kind of close to each other and basically be bumps on an almost convex landscape and stuff like that. So, I mean, I'll leave it to you to decide at the end of the talk whether this phase transition business, how close it is to real data concerns. But you know, to be fair, no matter how structured the signal is, if you add enough noise, something is going to break at some point. And
yeah, and I think an interesting question is of all the local minima, why does the algorithm typically find the local minima that is good enough for whatever prediction task?
I mean, the same is true of topic modeling. You know, that's also an iterative algorithm, which is doing a different kind of. It is a low rank matrix approximation, just with a different model of noise, really. Okay. Anyway, so all right. So, like I said before, we can't actually prove that this is exponentially hard because currently we can't really prove that anything is exponentially hard. You know, roughly speaking. But we could hope to show that a lot of our favorite methods fail. So what are some of our favorite methods? Well, today's talk is about spectral-ish algorithms, whatever that means. But what else do? We do Monte Carlo, where we would try to move around in the space of possible V's. Maybe you could show that Monte Carlo, if you initialize it randomly, gets stuck in some area, and because I'm a physicist, I draw things like this, and that it has to get over some energy barrier, which in thermodynamics would be a probability bottleneck, so that it would take exponential time to get over here to find the accurate states over there. That's something that you could prove about Monte Carlo. Another example would be message passing algorithms like belief propagation. Maybe you could show that it almost always goes to a silly fixed point, which doesn't tell you anything, and so on. But today's talk is specifically about showing that low-degree polynomials cannot solve this problem. What do I mean by that? Well, when you do PCA, what are you really doing, right? In fact, you might literally be doing this to find the biggest eigenvector of a matrix. You would just take a high power of that matrix and look at its trace, right? And as you power it up, eventually it's growing at the rate of its largest eigenvector, and the others are mattering less and less. And of course, the trace of a matrix, let's say this is just a matrix, the trace of, say, the third power of the matrix. Well, by the way, graphically, it looks like this. It just means taking 3 copies of the matrix and then summing over these 3 indices, right? That's what the trace is. But this is also the sum of the third powers of all of the eigenvalues of the matrix. And as you go to higher and higher powers of the matrix, looking at bigger and bigger loops, well, eventually what really matters here is just the largest eigenvalue lambda. And in fact, doing this to the log nth power is sufficient because there are only n eigenvalues. So the other ones go, you know, then this is really dominated by the biggest one. Good. But notice also, I mean, what is this thing? And I know I'm saying this 18 times, but this is literally a polynomial, a cubic polynomial of the entries of the matrix. Okay. So what I'm trying to say is that spectral algorithms like PCA are, you know, can be viewed as a part of a larger universe of potential algorithms which compute polynomials of reasonably low degree, maybe a little bit more than constant, maybe log n, but some reasonably low degree polynomial of the data of your input. So what I'm going to prove to you, or sketch a proof, is that no low degree polynomial can solve this problem in this range. And yes, good news is that there are low degree polynomials that work in this range. In fact, we were not the first to prove this, but of course, you know, Our proof has the benefit of being more recent. And also has, I think, a beautiful mathematical structure that is maybe renders the thing simpler. So, good. All right, a little bit more to tell you. And again, everything I'm saying is only in the spherical prior. Why? Well, you know, everybody knows that the trace of a matrix, which of course is this, there's the trace. Right? The trace of a matrix is a basis-independent thing. Why is that? Well, because if you took your matrix and you put an orthogonal matrix here and another orthogonal matrix here, wait, shouldn't one of these be transposed, you say? Free your mind. It is only our arbitrariness of sending some legs to the left and others to the right, which makes you think it needs to be transposed. It would be better to say that, you know, it sort of goes like this, because what's really happening is that both of these vectors coming out are being, I mean, after all, right? I mean, a matrix is also an n-squared dimensional vector if you flatten it, right? The goal here is to never, ever have to say, wait, is that a row vector or a column vector? And which one do you mean when you put the little t next to it? The goal is to never use that notation again, okay? Good. So, of course, what happens when I put the same orthogonal basis change on both legs here is they come down here and they cancel each other out because they're heading in opposite directions, or in the language you used before this afternoon, the transpose of an orthogonal matrix is its inverse. So then we would get the identity matrix, which is, after all, what we mean by a wire or a line in one of these diagrams. Okay? Good. So more generally, if I take any tensor network, here's my personal favorite. Okay, so little tetrahedron or complete graph of size 4. So this is a nice thing you could do and calculate. It would be a fourth order polynomial of the entries of a three-legged tensor. Well, if you change basis everywhere, what that means is that on every outgoing vector here, coming out of each of these vertices, you put the same orthogonal matrix, but again, they all cancel. Okay. So these objects, these traces or contractions of tensor networks or whatever you like, they're all basis invariant. Here's a lovely, lovely fact which goes back to Hermann Weyl. All polynomials of a tensor, which are basis invariant, which stay the same if you rotate by the same orthogonal matrix on every leg, are linear combinations of these. Okay, so this and its friends, they can be multigraphs, by the way. So here's one, here's another one. This, etc., these span the space of all orthogonally invariant fourth order polynomials of a three-legged tensor. Okay. Why is this important? Because I have chosen to study a version of this problem where everything is orthogonally invariant. The prior of the signal is, the noise is, okay? Therefore, any low degree polynomial that solves this variant of this problem might as well be orthogonally invariant. In other words, it would have exactly the same average performance if you spun it around by some random basis change.
So can you give it also if the group of symmetries is different, then what would be the invariant? What would be the other representation?
If they were orthogonal, see, like, sorry, if they were unitary, like when you take the inner product of two complex vectors, you have to tell me which one is on the left because that's the one that gets complex conjugated when you put them together. So if these were complex vectors, we would have to put arrows on them to indicate which way they were going. There we would have to pay attention to, is this a vector or a dual vector? Or in general relativity, contravariant or covariant index. Yeah, okay, good. But everything here is real and everything is symmetric, so I don't need to decorate the edges. Also, if these were not symmetric tensors, then I would have to put a little gadget here which told you, you know, which edge was connecting to which index. But if everything is symmetric and real valued, then I can just use unlabeled, undirected graphs, which is why I chose to look at that version of the problem. Okay, good. So that would be a different noise distribution. Yes, we could do that. That would be the sum of many of these. Yeah, so yes, people do think about Wishart random tensors. Okay, so since this problem is orthogonally invariant, and since these diagrams span all the low degree polynomials which are orthogonally invariant, if I can prove to you that no small diagram, or more generally, no linear combination of small diagrams solves this problem, I have proved to you that no low degree polynomial does. And I've done it in a beautiful graphical way. Now you know why this is a chalk talk, because it would be a nightmare for me to actually make all these freaking diagrams on Graphel or whatever, and it would be more boring anyway. It would be boring for you and frustrating for me, and nobody would be happy. Okay, good. So let me erase a couple of things. I think you're really going to get a satisfaction. This is going to be the best version of this talk ever, which is good because I'm giving it at Harvard tomorrow, and I don't know if they'll be as friendly. So this is a good setup. All right. Let me first try to show you that a single diagram of this type isn't going to work if lambda is much less than n to the minus p over 4. Okay, it's smaller than any constant times n to the minus p over 4. All right, let's first get a little bit of practice. You know, this thing, let's calculate the expectation of this thing, its average in the null model where these are all just Gaussian noise. Okay, how are we going to do that? Well, again, what do I mean? Let's get rid of these u's. What I mean is you put a bunch of indices on here, I, j, k, l, m. I already used t and p, and there's really a shortage of letters. Somebody should do something about that. Q. And I put a copy of my tensor at every place, and let's say it's just the noise, okay? So then this is the sum over I, j, k, l, m, and q of w, there's one there, I, j, k, and another one, j, l, m, and you get the point, right? K, m, q, and I, l, q. Okay, good. Now, each of these, for a given tuple of indices here, these are independent Gaussians. So what is, I don't know if you like this notation, but what is the expectation of this thing over the distribution of Gaussian tensors? Well, in order to contribute a non-zero amount to this sum, only certain tuples here, only certain combinations of these 6 indices will work. Why? Well, because, for instance, suppose that these have nothing to do with each other except that they share a couple of things in common. Well, if these are independent and they all have mean 0, the whole thing would be 0. Okay. In order to contribute, these things better be equal and come in pairs, for instance. So anything where ijk and jlm are the same triple of indices will contribute the average of the square of that, which is 1. Okay? All right. So what I'm saying is that the things which contribute, and this is why it was so important for me to have 4 colors, The things which contribute are things where, for instance, j equals q and maybe L equals K, so that, oh, that's not what I meant. This is the same as that, and this is the same as that. And now actually, this can be different from that. But now note that every vertex has a partner with the same three colors of edges on it. Namely, this and this both have black, red, and blue. This and this both have black, blue, and pink. Okay? So this is one of the ways to color this. So maybe this has, the blue ones could be I, the black ones could be J. So we would just have, we would just be summing over I, J, K, and L, say. And every such tuple would contribute 1 to this sum. In fact, so then you're like, oh, well, that's interesting because there are roughly n to the 4th tuples like this because there are n degrees of freedom. There are n different colors here. So this suggests that this grows like n to the 4th. And then you would think, oh, yeah, you know, there are 3 different perfect matchings of this little tetrahedron. So maybe there are actually 3 arrangements of colors like this. So maybe this grows like 3 times n to the 4th plus some little correction terms, and you'd be right. Okay. So, I mean, this is all really fun, right? So, I mean, anytime we start out with Gaussians and orthogonal matrices and we end up coloring little graphs and doodling, that's always a win. So here's a little problem for you. And it sounds like one of those first semester computer science problems. I give you a graph. It happens to be 3 regular. Everything has exactly 3 edges. And what is the largest number of colors that you could put on the edges of the graph so that every vertex has a partner with the same edge colors? Well, turns out this is NP-hard. Okay. You know, my co-author Tim Kuniski. By the way, this is all joint work with Tim Kuniski and Alex Wine, and there's ongoing work also with Max Jurdy. Okay, sorry. So this paper appeared in, or will appear in, Fox this year, which is a computer science conference. Anyway, so even figuring out what power of n does this grow as is NP-hard. Then you're thinking, well, wait, can't we just compute this by Monte Carlo sampling? Oh, well, you can try, but it's an exponentially, it's a high degree, it's a high dimensional integral, and you know those can be hard. And so, yeah, this one is hard. Okay, all right, good. So that gave us a little practice just in computing the average of this in the null model with only noise. Good. Now, how might I argue that, let's say I want to argue that this particular diagram is not good at solving the problem when the signal to noise ratio is below that point. What do I mean? Well, by the way, we could use these diagrams. I initially said I want an estimate of V. Well, if you want a vector, you should do something like this, a diagram with one leg hanging off it. If you contract all the other edges, this will produce a vector. But here I'm going to do something even simpler. I'm just going to ask, can you solve the detection problem, or what our statistician friends would call the hypothesis testing problem? Can you even tell the difference between this model and the null model? Okay. So I want to argue that this little quantity cannot. What does that mean? It means that there is not a big difference in the distribution of the value of this between those two models when lambda is less than that point. So if you computed this, you'll get roughly the same distribution of answers. Okay. So how is that going to work? Well, I claim that we need to compare two things. One is the difference in the expectations between the structured model minus the null model. In other words, how much does adding this pattern to the noise change the average? That's one question. But the other question is, what is the variance in the null model? Because basically, if the null model has a really broad distribution, then shifting that distribution over a little bit isn't going to help you very much. Okay. Now, you could be thinking about higher moments and so on, but this is the level at which I'm going to do the analysis. Okay. Good. Let's compute this first, or at least part of it. Well, let's see. There is a copy of this, or let's call it this, at each vertex. Okay? Well, if you actually multiplied that out, it would mean summing over all of the binary combinations, where at some vertices you have this, and at others you have the noise. Right? That would just be multiplying out this product. But we're subtracting this off anyway. There are cross terms, but it turns out we don't care about the cross terms. Turns out all we need to worry about is the all signal term. What is that? That's where we have this at every vertex. What does that mean? Well, first it means that we have 4 factors of lambda, which are getting multiplied together. And the other thing is that coming out of every edge of every vertex is a copy of the vector, because that's what this tensor product means, v, v, v. And they meet other copies of themselves coming out of others. And when they hit each other, we get an inner product, which is the length squared of v, which is n. Okay. So the all signal term is simply lambda to the number of vertices. And now I'm going to write this down. Let's say we have a diagram with A vertices. In this case, that's 4. And B edges, in which case here, this is 6. And, oh, wait, 1, 2, 3, 4. Yes, okay, good. Right. And notice that in a p regular graph, where here p is 3, the number of edges is p over 2 times a. Okay? Because every edge has 2 ends. All right, good. So this here, I just showed you, if you don't worry about the cross terms, is lambda to the number of vertices times n to the number of edges. Good. Well, what's the variance? Well, remember, that's the second moment minus the square of the first moment. What's the second moment? The wonderful thing is that here is one copy of this. The second moment is just 2 of them. Right? This is another great thing about this graphical tensor calculus. If you want 2 copies of something, if you want the square of something, you just make 2 copies of it. So the second moment of this is the average of the square is just the average of this combined diagram. In the null model, and I showed you before, that has to do with coloring the edges that everybody has a partner. Well, one way to color the edges is to put 6 colors over here. I can't do that. And the same 6 colors over here. Actually, I did that pretty well. And then everybody is partnered with its counterpart in the other copy. And the number of colors is n to the b. So the variance grows at least as fast as n to the b. Of course, what we want to compare to this difference is not the variance, but the standard deviation, because that's how much things are getting shifted. So it's n to the b over 2. So this is small compared to that. This is large compared to that, thus making it hard to notice this difference if n to the b over 2 is greater than lambda to the a times n to the b, but b is p over 2 times a. So this is n to the p over 4 times a, which is greater than lambda to the a, and then this is n to the p over 2 times a, and we subtract that from both sides, and we get this threshold. Yay! Okay. Wow. So this is a lot simpler than the previous proof, which was found by brilliant people who I greatly admire, who are not me. What I don't have time to show you is, well, remember that we could consider linear combinations of these, not just one diagram. I've shown you one diagram doesn't work. But what if several diagrams were correlated and we cleverly subtracted some from others to push down the variance while still keeping the expectation difference? So if we could cancel out some of the variance, maybe we could still do it. Well, in order to show that that doesn't work for small diagrams, we had to invent a slightly different version of these moments, which are nearly orthogonal to each other in the sense that if you take the average of their product in this null model, you get something asymptotically zero. In other words, they're nearly uncorrelated from each other. And that means if you make a linear combination, the variances just add up. So you can't get that cancellation. And anyway, so that's the second talk.
And the other transition?
Oh, the other transition is a different argument, which is not original with us. Yeah, you mean the impossibility, the information theory impossibility. So, maybe your take home from this talk, if you didn't already know, there are these cool phase transitions and these statistical computational gaps. There is now, not just through this, but through a lot of the work of Cyril Schramm and Sam Hopkins and Alex Wine and Tim Kaniski and many others, there is now a technology for showing that low-degree polynomials cannot work, which eliminates everything which is kind of spectrally. It also eliminates a small number of steps of gradient descent, for instance. And it eliminates a small number of iterations of, it eliminates a small number of iterations of pair effect. Yeah, good point. So that's good. It's considered evidence for hardness in this regime. It's not the same as saying there's no polynomial time algorithm, but for many of these problems, spectral things are basically the only things we know. It applies also to semi-definite programming, which is a major family of algorithms, and so on. The other thing I want you to take home from this is that if you have a tensor of data, you should think about computing kooky sums of products of its entries like that. Maybe this will tell you something. You should consider computing things like what I had written up here before, where you are contracting things, but you're leaving one thing left over. And this is indeed an approximation to a kind of singular vector. And even this little diagram does work reasonably well above this threshold. In fact, any little diagram does, which is kind of cute. So I guess I'll stop there. If anybody wants to talk about free probability, which I promised to in the abstract, but this is already farther than I've ever gotten before. Okay, thank you very much.
Any questions for Chris, either here or online? So tell us about the probabilities, if there are no questions.
Oh, okay, great.
Short, 1 minute.
Axioms
of probability. Go ahead.
Okay, free probability is a kind of it's a sort of non-abelian generalization of it. So suppose you have two really big matrices, A and B. They're n by n, where n is enormous. They both have a bunch of eigenvalues. Suppose we add these two matrices together. Well, if their eigenvectors all lined up, that they're diagonal on the same basis, we would be adding up those eigenvalues. But I don't know anything about how their eigenspaces, their eigenvectors line up with each other. So effectively, I want to ask this following question. Suppose I take one of them or both of them and spin them around in n-dimensional space by a random rotation, and then add them together. Okay? So this sort of randomizes how their eigenvectors lie with respect to each other. Free probability lets us compute the typical spectrum of the resulting thing. And interestingly enough, when in the limit that n is large, that typical spectrum becomes concentrated. In other words, it becomes almost deterministic. It's almost like a kind of central limit-ish thing where that random rotation produces something which is very reliable. There are things called cumulants that add up when you do this. And we've written down what we think about the right notion of free cumulants for tensors. For tensors, you would take two tensors and do a random rotation on one or the other, and then add them together. And so then the question would be, what do all these diagrams turn out to be? And we and some people in France have been working this out. So, yeah.
That's interesting.
And I really, okay, so I encourage you to do the following. Make yourself a random Gaussian matrix, make a histogram of its eigenvalues, you'll see the semicircle. I also urge you to poke around and learn why it's a semicircle. I mean, it's gorgeous. Its moments are the Catalan numbers. I mean, you won't believe it. It's all so nice. It's like, chef's kiss. So there are multiple proofs. You really should check them out. And random matrix theory is beautiful. So, yeah.
So you use this technique, this diagrams in the paper, right?
Yes.
Yeah. What's the best resource for this kind of methodology?
I think our paper is a really good resource. I mean, so there are, continuing with the egregious name dropping or physics dropping. I mean, that doesn't quite, yeah, physics dropping doesn't sound quite right. So there are a number of high energy physicists who've thought about tensor networks of various kinds, because these are also basically Feynman diagrams. So again, that's total name dropping. But these vertices can represent different kinds of interactions, and they really are tensors, which say things like, if two particles come in with some momentum, then how often does a third particle come out of that collision with a certain momentum? This is, if anything, a much simpler version of all that, where we just have one kind of vertex. Although you can have different tensors at different vertices. And so Feynman diagrams are ways to do a kind of Taylor series, where you take some complicated thing and you write it as a sum of larger and larger diagrams, which, as you now know, corresponds to higher and higher order terms, higher order polynomials. And so that's, yeah, anyway, that's kind
of like recent development in Feynman diagrams.
Well, there's a guy named Gurau who has a paper on random, who has a whole book on random tensors, and there are some people, there's a cluster of people around him that are thinking about these things. And yeah, but I think some of our results are actually, even our results on these tensor networks are new. So not all of them, some of them.
Any questions? No? Thanks. He's going to be downstairs for conference. you guys this. Thank you.
And tell your favorite editor at Quanta that they really ought to run an article on this. I mean, data science, Feynman diagrams, what's not to like?
That's great. That was very good. That was excellent. Yeah, the notion that I can't have any combination of these things. I like impossibilities.